We are the group 3 and we will be discussing noise. So first, let's start with its definition. In electrical terms, noise may be defined as any unwanted introduction of energy tending to interfere with the proper reception and reproduction of transmitted signals. So, to make things clear, let us make use of an illustration. So, effects of noise on signal. As you can see here, this is what signal looks like without noise. And comparing it with the second illustration, you can see that there is an interference with the signal because there is noise. Noise is actually a random energy that interferes with the information signal. As you can see here, this is what signal looks like without noise, and this is what noise looks like. And putting it together, a signal with noise has an interference. So it looks like the first one, but it has noise. Why is it important to study the effects of noise? Today, telecom networks handle enormous volume of data, and our ability to recover the required data without error is inversely proportional to the magnitude of noise. This simply means that the higher the magnitude of the noise, then the lower our ability to recover the required data without error is. That's why it is inversely proportional. What steps are taken to minimize the effects of noise? Special encoding and decoding techniques used to optimize the recovery of the signal. Transmission medium is chosen based on the bandwidth. End-to-end reliability requirements, anticipated surrounding noise levels, and the distance to destination. And lastly, elaborate error detection and correction mechanisms used in the communication systems. So what are the results of noise? Hiss or static, snow, confetti, signal loss, bit errors. So most commonly we see these results of noise in our television, like what we have watched earlier. So what are the kinds of noise? So there are two kinds of noise. The first one is the correlated noise, which implies relationship between the signal and the noise. It exists only when signal is present. On the other hand, uncorrelated noise, it is present all the time, whether there is a signal or not. So in the correlated noise, there should be a signal, and uncorrelated noise is present even if there is no signal. So for the correlated noise, form of internal noise that is correlated to the signal and cannot be present in a circuit unless there is a signal. So as defined earlier, there should be a signal. Produced by nonlinear amplification. Hence, all circuits are nonlinear, therefore they all produce nonlinear distortion. Nonlinear distortion creates unwanted frequencies that interfere with the signal and degrade performance. So there are two kinds of correlated noise. The first one is the harmonic distortion, and the second one is the intermodulation distortion. So for the harmonic distortion, this occurs when unwanted harmonics of a signal are produced through nonlinear amplification. Harmonics are integers multipliers of the original signal. So the original signal is the first harmonic. A frequency 2 times the fundamental frequency is the second harmonic. 3 times is the third harmonic, and so on. So as defined, you can see here that this is the first harmonic, and then the frequency 2 times the fundamental frequency is the second harmonic, 2F1, and the third is 3 times, so it goes on. So for the intermodulation distortion, Intermodulation distortion is the generation of unwanted sum and difference frequencies produced when two or more signal mix in nonlinear device called cross products. So as you can see here, these are the frequencies, the fundamental frequencies. But then, since there's an unwanted sum and difference frequencies produced by two or more signal mix, so this is what the intermodulation distortion looks like. This is the output. So uncorrelated noise has two types, which is the external, which means the noise whose sources are external to the receiver, and internal, which means noise created within the receiver itself.
Types of external noise. Atmospheric noise. Atmospheric noise or static is caused by the lightning discharges in thunderstorms and other natural electrical disturbances occurring in the atmosphere. Extraterrestrial noise. There are two types. There is solar noise and cosmic noise. Solar noise, in normal condition, there is a constant noise radiation from the sun simply because large body at a very high frequency. Cosmic noise, stars radiate solar frequency noise in the same manner of sun. The noise received is called thermal noise and distributed uniformly over the entire sky. Man-made noise. This noise ranges between 1 to 600 MHz in urban, suburban, and other industrial areas, and is most prominent. Sources of such noise: automobiles and aircraft ignition and electrical motors, switching equipments, leakage from high voltage lines, and a multitude of other heavy electrical machines. From the slide itself, you can see that a man-made noise is being made from the band. This is a good example of a man-made noise. Now, on with the types of internal noise. Shot noise. These are caused by the random arrival of carriers at the output element of the electronic device. It is first observed in the anode current of vacuum tube amplifier. The current carriers are not moving in a continuous steady flow. They are randomly varying and superimposed onto any signal present. Sometimes it is also called transistor noises. Shot noise is given by the formula IN squared is equals to 2I DC Q E B sub N ampere squared. The DC current is amperes. The Q sub E is the magnitude of the electronic charge, and the B sub N is the equivalent noise bandwidth in hertz. Thermal noise. It is associated with the rapid and random movement of electrons within a conductor due to thermal agitation, present in all electronic component and communication systems. It can also be referred as white noise. If you listen to live bands, you will notice that there are always static from the speakers. That is due because of the thermal noise. The hotter the amplifier becomes, the more white noise it produces. That is why there is such a thing called thermal noise. It is a form of additive noise, cannot be eliminated. You can only eliminate this kind of noise if you cool down the instrument or the amplifier itself. It increases in intensity with the number of devices in a circuit. In 1928, J.B. Johnson have proven that noise power generated is proportional to the temperature and the bandwidth. We can see in this formula that the power generated is equals to constant times the temperature times the bandwidth. The constant K is the Boltzmann's constant, which is 1.38 times 10 raised to negative 23 joule per Kelvin. This is Bert Johnson and Harry Nyquist. Uh, this type of noise was first measured by John B. Johnson at Bell Labs in 1926. He described his findings to Harry Nyquist, also at Bell Labs, who was able to explain the results. Noise power can also be modeled using the Thevenin equivalent circuit or the Norton equivalent circuit. This is the circuit representation of the noise power, and this is the formula derived given the resistance. We can by deriving from the circuit before in this slide, we can derive the formula, arriving to a formula of Vn is equals to 4 Vn is equals to square root of 4k TBR, where Vn is equals to the RMS noise voltage, R is equals to equivalent noise resistance, T is the temperature of the conductor in Kelvin, and B is the bandwidth of the noise spectrum.
For the continuation of types of internal noise, next is flicker noise. It is a type of an electronic noise with 1 over F or pink power density spectrum. It is therefore often referred to as 1 over F or pink noise. It is the one appearing in transistors operating at low audio frequencies. In carbon and thick film resistors, flicker is called excess noise because it is higher in amplitude than thermal noise. It can be reduced by using wire wound resistors. And another way to mitigate it is to minimize the DC component. It occurs in almost all electronic devices, and it has a variety of different causes, although these are usually um, related to the flow of direct current. Next is transit time noise. Transit time is the duration of time that it takes for a current carrier, such as a pole or current, to move from the input to the output. The devices themselves are very tiny, so the distances involved are minimal. The time it takes for the current carriers to move even a short distance is finite. At low frequencies, this time is negligible, but when the frequency of operation is high, then the signal being processed is the magnitude as the transit time, then the problem can occur. The transit time shows up as a kind of random noise within the device, and this is directly proportional to the frequency of operation. It occurs within a transistor when the time for an electrical pulse is close to the period of the amplified signal. This causes the transistor to offer reduced impedance to noise. And this phenomenon is increasingly apparent at higher frequencies. Next is burst noise. Burst noise is consists of sudden step-like transitions between two or more discrete voltage or current levels as high as several hundred microvolts at random and unpredictable times. And each shift in offset voltage or current often lasts from several milliseconds to seconds and sounds like popping popcorn if hooked up to an audio. It occurs in semiconductors and it's also called popcorn noise, impulse noise, bistable noise, or random telegraph signal noise. Next is noise factor and noise figure. Figures of merit used to indicate how much the SNR or signal to noise ratio deteriorates as a signal passes through a circuit. Essentially, um, essentially the measurement assesses the amount of noise in each part of the system or the system as a whole introduces. This could be the radio receiver or an RF amplifier, for example. Uh, if the systems were perfect, then no noise would be added to the signal. And when it passes through the system, and the signal to noise ratio would be the same at the output as the input. As we all know, this is not the case, and some noise are always added, which means that the signal to noise ratio or SNR at the output is worse than the signal to noise ratio at the input. The noise figure is simply the comparison of the SNR, the input, and the output of the circuit. Um, Noises is usually expressed as a power because the received signal is also expressed in terms of power. By knowing the signal to noise powers, the signal to noise ratio can be computed. Noise factor is the measure of degradation of the signal to noise ratio in a device. Uh, it is the ratio of the SNR at the input to the SNR at the output. Since the SNR at the output will be lower than the SNR at the input, the noise factor is always less than 1. The lower noise factor results in better performance of a device. And according to the equation, F is equal to the input of SNR and over the output of SNR. Next is noise figure. Noise figure is a number by which the noise performance of an amplifier or a radio receiver can be specified. The lower the value of the noise figure, the better the performance. Essentially, the noise figure defines the amount of noise an element adds to the overall system. It may be a preamplifier, mixer, or a complete receiver. Often, the noise figure may be used to define the performance of a receiver, and in this way, it can be used instead of the signal to noise ratio. In view of this, of its widespread, applicability, noise figure is a particularly important parameter for a wide variety of radio communication systems, from fixed or mobile radio communication systems, two-way radio communication systems, and satellite radio communications. Noise figure is designed as a ratio of the signal to noise power supplied to the input terminals of a receiver or amplifier to the signal to noise power of the output or load resistor. Um, the noise figure F is also called the noise factor, and it can be expressed with the expression of Si over Ni, which is the input of signal to noise ratio and the output of signal to noise ratio, in which in the equation express is equal to 10 log F, and to uh, uh, to extend more is 10 log xi over ni over x so over no. For ideal noiseless network, the noise figure will be 1, in which introduces no noise of its own. And next is for a network that produces noise, the output the output signal to noise power will be lower than the input value, and so the noise figure will exceed to 1. And that concludes our discussion about noises.